Hello and welcome to this lecture on Shear Center. Now, before you come to a Shear Center, please have a look at my previous video where I explain about shear stress distribution on beams. So, coming to Shear Center, the Shear Center is it's a very peculiar property. It basically refers to a single point on your beam, and what that point is, we'll come to soon. Um, where we can start with talking about shear center is what we can do is we can first have a look at this particular channel section beam that we have over here. This is the centroidal line, and I'm applying my external load such that it passes through my centroidal y-axis. Okay, so I take a section right where that load is acting, and let me just have a look at that cross section over here. So I see that no, I have applied a load through the centroidal axis. So my load is kind of probably acting over here. This is my center of gravity. This is my external load which is acting. Now what I would links like you to remember is you do remember that now when you have a, for example, when you have a rectangular section, for example, if you have a rectangular section, you know that now once there's an external load acting over here, now your shear stresses or your shear flow is going to be acting. This is how your shear stresses act on the face. But when you have a section like this, which is not it's not a single phase, it has one, two, three different phases. So any load which acts over here, no, it's going to it's going to make your shear stresses to follow that path. So this was explained in my previous video. You can have a look at that. So anyway, so that's what's happening over here, and I have shown this shear flow over here in the terms of this green arrow marks. So what I would like to next do is I want to check the equilibrium for this cross section in its own plane. So the summation of moments in the plane of the cross section. The summation of the moments in the plane of the cross section is nothing but, let me take it about the centroid, about CG. Okay, so this is at a certain distance x bar. This is at h by 2, f3 is at h by 2. So the summation of moments given P will not come because P is already acting on the CG. The summation of the moments gives me F1 and F2, both of this act clockwise through a distance of h by 2. So I'll give a minus sign for clockwise. And also this F2, which acts on the web, even that is also clockwise. So minus, oh, this is F3, minus F2 into the centroidal distance x bar. So this is minus, this is minus. I see that this is not equal to 0, which means there's no equilibrium in of the plane of, or in the plane of the cross section. There's no equilibrium in the plane of the cross section. There's no equilibrium in the plane of cross section. Okay. Now before proceeding, I would just like to draw your attention to a normal beam. Okay. So if this is, and I mean, it's a simply supported beam. Okay, and if I have a certain load, and if I get the bending moment over here, so because of the bending moment in this particular beam, I see that my member will actually rotate like this. Okay, because of the bending moment or the moment over here. So this moment is actually a moment acting in the, or acting about the, let me say, yeah, about the longitudinal phase, longitudinal section. This moment acts about the longitudinal section. That's why you have your rotation on the longitudinal face. So you extend the same concept to this. This moment is not on the longitudinal section, it's on the cross section. This moment is on the cross section. So therefore, just like how your longitudinal section would rotate, your cross section would also rotate because of the unbalanced moment acting, which is equal to this value. So it's clockwise. So I may have a clockwise rotation. Okay. So I may have a certain clockwise rotation. Okay. So this is a rotation of the cross section face, or the better way to call this is twisting or torsion. This is the better way to call this is twisting or torsion. So I see that even if I apply a load through the CG, if you have open sections like this, like a channel. So if you have open sections like a channel, you will see that even if you have the load acting through the centroid, you would still have twisting of the cross section. You would still have twisting of the cross section, except for one particular example. Okay, so based on this explanation, I'll try to tell you what is meant by a shear center. So now, if you understand this, that there that we are dealing with rotations or rotations of the cross section, or in other words, a twisting, it is easy for us to define what is meant by a shear center. Now, what I can tell you is, if I don't want twisting to happen, I obviously know that my load should not be here. Okay, why do I say that? Now I found that my external load in which I was acting over here, it did not counteract my shear flow. Okay, so about the centroid, the shear flow causes clockwise movements. So the only way to avoid twisting is in case my in case my external load caused a anti-clockwise moment. Okay, so that means my moment should actually lie to the left of the CG. So probably it could either lie here, it could lie there, either or lie here. It should be somewhere to the left. That's all that I know. Okay, that is all that I know. Now take the two cases. Let me call this as case 2. Let me call this as case 1. All right. Now, what happens is, now if I take case 1, I would see that this F1 and F3. All right, F1 and F3 cause a F1 and F3 cause a what is it? It is this clockwise. Now, if now P, which acts over here, P is here and F2 is here. Now this also becomes clockwise. Okay. Now this becomes clockwise as well. So even though I have moved it to the left of the CG, if I do summation of moments now, this is clockwise. The couple of F1 and F3 is also clockwise. The couple of P and F2 is also clockwise, and therefore this also will not give you equilibrium. So therefore I move to option 2. So if I investigate option 2, in that case I will see that I will find that if I place my load at position 2, which means to the left of the cross section, to the left of the web as well. So in this case, F1, F3 go clockwise, and F and P and F2, these go anti-clockwise. Okay, so the F and F3 are separated by H. This and this are separated by some distance. Okay, so I have to So I have to place my P such that this P P times E should be equal to F1 times um, H. Okay, I should place it in such a way, or no, no, let me not write it like this. I should place P in such a distance such that the couple caused by F1 and F3 separated by a distance of H should be equaled or should be balanced with the couple created by P and F2. And this distance, the location where your P should be placed, is known as your shear center. The location where your P should be placed is known as shear center, so that it avoids twisting. So shear center is the point on the cross section where the load should be placed in order to prevent twisting. So this is what is known as a shear center, and that shear center is usually measured by a distance c. This can be measured in two ways, either from CG or from web center, depending on what your application is. In different places they use different locations to measure your shear center. Now, if in case it was a closed section like this, if I take moments about the centroid, I see that this whole thing. Now, this whole thing is actually, if I take it about, say, any point. Okay, now if I take it about some point over here, I see that all these things are causing, I mean, it is having a continuous flow of your, what to say, it has a continuous flow of a shear. So in this case, if your P, so in case your, if you keep your load anywhere else except at the center, you will not, you will again face the same issue as you faced over here. So in general, what we say is for bisymmetric sections, sections, the shear center and centroid coincide. All right. So anyway, this is how we draw the shear flow. But anyway, this could as well have been drawn with arrow marks coming up from here and going down over here. Okay, it could have been drawn in either fashion. So anyway, so this is what is shear center. Now let's look at how to find shear center for a very gentle section like this hat section. And trying to find the shear center, no, for open sections, we generally try to use generalized coordinates. Okay, we don't, instead of going by x and y, it's a shear flow. It starts at one point, ends at another point. So I keep my coordinate system such that it follows the path of my shear flow. Okay, so this is how we started. Also recollect that we have to keep using this formula, VQ by IT. We are assuming that our load is about the centroidal, I mean I'm sorry, not here. We don't know where we want to place the load. It's acting through the global y direction. Okay, the load is acting through the y direction. This means I'm going to be concerned with IXX. Okay, so this is one thing. This is the shear stress. And of course, to get shear force, you just need to know integral over area of the shear stress. Okay, so these are the two things that you will be using now. I'll just label my parts as 1, 2, 3, 4, and 5. Okay, this is how I want to label my parts. Now, starting one by one, if I come to part 1, so part 1 is the one at the bottom. Okay, this part, which is of center to center dimension C, this is T, and we are of course measuring S from here. Okay, and you also know that Q here, which you need, is nothing but the first moment of your area up to this point. Okay, this is the centroid of this particular uh, section S. This is the centroid of the section S, and the distance from here to that section. Okay, so from here to here is h by 2, and then I have plus C. So the distance is, so up to here the distance will be h by 2 plus C, which is this one, minus S by 2. Okay, this is centroidal distance. So Q equals AY bar. A is nothing but S into T into H by 2 plus C minus S by 2. Okay, or I can write this as ST by 2 into H plus 2C minus S. Okay, and therefore tau of S equals V q by 2 V by, I'll just use I instead of IXX for simplicity, into ST by 2 H plus 2C minus S, which also equals in simply Vs by 2I into H plus 2C minus S. So this is my expression for the shear stress. So of course, where S is 0 at the starting, so tau of S is equal to 0 at S equals 0, and it will also be equal to Vc by 2I into H plus C at S equals C. Okay, which means at this particular point, this will be the value of the shear stress. Okay, so I want also the, so in order to find the moment caused by this whole shear force, I need to find the total force inside this element. So the total force inside this element is given by, so if I say dv1 equals tau 1, let me, this is tau 1 of S ds equals which implies v1 equals integral of 0 between 0 to c tau 1s ds, okay, which is also equal to 0 to s, sorry, 0 to c, 0 to c vs v into s by 2I, v into s by 2I into h plus 2c minus s into ds, or v um, into sorry into this is sorry, this is shear stress. So force is shear stress into area is so this is d, if this is ds, this is t, so it will be t into ds. I forgot the t. Okay, into tds, so which gives me vt by 2I, and integrating this whole thing over s, I get hs square by 2 plus 2cs squared by 2 minus s cube by 3 between 0 to c, giving me the total force in element 1 V1 is nothing but Vt by 2I into Hc square by 2 plus 2c cube by 2 minus c cube by 3, or equal to, in I can simplify it and write it in general as Vt square by 12I into 3h plus 4c. Okay, so this is element number 1. Next I go to the flange, which is element number 2. At element number 1, you should know that at its start, tau 2 of s should be equal to tau 1 of s. Okay, so whatever is the value of the shear stress at the end of, whatever the shear stress is there at the end of 1 should be the shear stress at the beginning of 2, because it is the same point. So therefore, the at the starting of T2, the shear stress should be equal to whatever was it at the beginning of, or the end of 1. Okay, so just remember that. Now as far as element 2 is concerned, let's once again, so this is the element, yes, goes, travels this side. All right, so s travels this side. So you can keep here, you can do the integration between s equal to 0 and s equal to b. You can even do it from, because it's already traveled a distance of c up to here, it's already traveled a distance of c up to here. So therefore, when it reaches this point, s would have traveled c, and up to here is b plus c. Okay, so either you can do 0 to b, or even if you do c to c plus b, you will get more or less the same. But anyway, this causes more terms, let's not do that. So between s equal to 0 and s equal to b, I have to do my whole process again. And the distance to the centroid of this element from the x-axis axis is h by 2. Okay, the distance to the centroid here to here is h by 2. Okay, so that is h by 2. So q, let me say q2, because this is element number 2, q2 is nothing but s into t into h by 2 as far as only this element is concerned, or equal to s th by 2. Now tau 2 of s equal to whatever comes from this, whatever comes from this, which is nothing but if I put it into v cube by 80, I will get vsh by 2y. And also whatever was there at the end of element number 1 should be present there in element number 2. So you have to include the whatever shear stress was there at the end of element number 1. So at the end of element number 1, which means at s equal to c, we had this as the value of the shear stress at the end of element number 1. So that value you have to add vc by 2I into h plus c, which gives me v by 2I into sh plus ch plus c squared. Of course, if I do s equal to 0 in this, which means at this point, when s equal to 0, I will get the same as what I got over here. Okay, I'll get the same as tau 1 of s, and okay, I'll get that same value again. And at s equal to b, at s equal to b, which means at this location, I get tau 2 of s equals v by 2. Just substitute b in places of s, bh plus c h plus c squared. Okay, so similarly now I want to find what is the force in element number 2. So now it is from 0 to b, integral between 0 to b, vt by 2I, just like what I did over here. Basically, I'm just going to use uh, dvl equals tau 2, dv2, sorry, dv2 will tau 2 of s into t into ds, and I'm integrating this. Okay, I have already tau 2 of s over here. So vt by 2I into sh plus basically this expression ch plus c squared ds. So simplifying this, I get vt by 2I into h s square by 2 plus chs plus c square s 0 to b, or vt by 2I into hb square by 2 plus chb plus c square b. Okay, or more simply vt by 4I into hb plus 2ch plus 2cb vt vtb. Okay, Mr. B there. Okay, so then I go on to element number 3, which is the web. So element number 3, the web. What is element number 3? Again, for convenience, I start my s from here. Okay, from s equal to 0 to s equals h. Okay, and uh, this is my centroidal axis. Okay, so to the distance to the centroid of my s element is nothing but, so so um, this is nothing but h minus s by 2. This is nothing but h minus s by 2, because it is nothing but h by 2 minus s by 2, so h minus s by 2. Okay, so this is what I have. So then again, doing the same process again, q3 equals area is st into h minus s by 2, which gives me tau 3 of s equals nothing but vsh by 2I into s minus h. And just like how we said for the previous element, that at the start t2 of s should be equal to t1s, here also at the start, so here also at start, or t2 t3 s start should be equal to t2 of s what was there at the end of t2. Okay, so that should be true here also. So at the end, t2 of s is this value, v by 2y into bh plus c squared. So plus v by 2I into bh plus ch plus c squared. Okay, or in other words, simplifying it, I get v by 2y into it's a little big, sh minus s squared plus bh plus ch plus c squared. Of course, when s equal to 0, which means at this point at s equal to 0, so this and this will go, and I get v by 2 into bh plus ch plus c squared, which is equal to tau 3 of s is equal to tau 2 of s end. Similarly, at s equal to h, which means at the top, at this location, remember that the top of this is nothing but, remember the top of this is nothing but the end of this flange. This is a symmetric hat section. So whatever was the stress here will be the stress over here also. So whether I do for at the bottom or at the top, I should get the same value of shear stress. So if I substitute H over here, then also I get this whole thing going to 0, and I will get the same T3 of S will be equal to T2 of S at the end. Okay, so this should always be satisfied such that at both ends, at the junctions, the shear stresses between two elements should be the same at every single junction that you have. And proceeding, dV3 equal to nothing but tau 3 of S into TdS. Okay, giving me V3 equals, let me take V and all these common things outside, 0 to H this time, SH minus S squared plus BH plus CH plus C squared ds, giving me so just do the integration for this whole thing. You will have S square H by 2 minus S cube by 3 plus BHS plus EHS plus C square S. Okay, and then substitute the value of H and 0. I'll write the final equation alone. So I will get what I'll be getting VT H by 2I into uh, this is after taking H common outside, into H square by 6 plus BH plus CH plus C squared. Okay, so RVTH by 12 into H square plus 6 BH plus CH plus C squared. Okay, now what I'm going to do is I have, because of the symmetry, I know that V1 equals V5, V2 equals V4, and then I have V3. Okay, which basically I'm meaning that this and this are equal in magnitude, this and this are equal in magnitude, and then I have this. Okay, so now in the cross section, that I had, I'm going to take moments about a certain point. So this is V1, V5, V2, V4, V3. Okay, now I'll apply the same principle as I told over here. uh, I'm going to find the moment within the plane of the cross section, and I want to equate it 0 because the shear center means the place where the external load should be applied such that the twisting is prevented, or in other words, the moment acting on the plane of the cross section should be 0. Okay, so I can take any point, but I'll choose particularly the center of the web, because when I take moment above the center of the web, V3 will vanish in the equation. Okay, the moment component due to V3 will vanish if I take moments about this point. Okay, so what I'll now do is, um, let me just guess that the load or should be applied here to prevent twisting, or let me just assume that E lies over here. Okay, then I also have h by 2 distance for V2 and V4, and B distance for V1 and V5. Okay, so this is how I'm going to take summation of moments about the point O. Okay, so sigma MO equal to 0 implies I should have this P into E should be equal to, P into E is anti-clockwise, V1 is clockwise, sorry, P, V1, V5 are all anti-clockwise. Okay, so P into E plus V1 and V5 are in the same anti-clockwise sense. So V1 plus V5 into B should be equal to the clockwise moments, which are V4 and V2. V2 plus V4 into H by 2. All right. So, or instead of P, since I know that this is a beam, uh, since if it is a beam, so I want to rather talk about the value of the shear force in the beam rather than P. So let me just, instead of saying P, let me just say V, because we had started with V over here. Okay, we were talking everything in terms of V, which is the shear force acting on the particular point. So in terms of V, if I write everything in terms of, I should have written in terms of V. I'm sorry that I wrote it in P by mistake. Okay. So anyway, so if you have this equation, what I know is that V1, V5, V2, V4, all of them are in terms of the shear force at the particular section. Okay. So V will get cancelled out. Okay. V will get cancelled out. But anyway, as of now, let me write V times E equals, I'll just substitute for V1, V5, V2, and V4, whatever we found above. So what I will have is for V2 and V4, I have Vt by 4I into Hb plus 2Ch plus 2Cb. Okay, and there's a H by 2, and H by 2 cancels out, and there is a 2 times of this whole thing, so I get H over here minus, then minus this part, minus Vt by um, I get Vt by mm, Vt by 12I into, there is 2 times of V2 and V4, so whatever I got I multiplied by 2. Because V2 and V4 are same, I can write this as 2V2 or 2V4, so I'll just multiply it by 2. So here I had inside, where is it, 3H plus 4C, but now I'm going to have V1 plus, oh, just a minute, just a minute, yeah, I'm right. Okay, yeah, so V1 and V5 is nothing but 3H plus VTC square by 12 into 3H plus 4C. Since I have V1 plus V5, I can just multiply this by 2. So I have 6H square C, 6H square C plus 8C cube B. Okay, square, forgot a B over here. Okay, so these are my two parts. So basically, I'll just, in case you're confused till now, I'll just once again just tell you what I did over here. Simply, V1 and V5 are equal in magnitude. So substitute for V1, added with V5, multiplied by H. No, sorry. I mean, this term corresponds to V2 plus V4. Okay, I'll just make it. So this 2 corresponds to V2 plus V4 into H by 2. And this 2 corresponds to V1 plus V5 times B. Okay, so just look at your value expressions derived above, substitute them, then you should be getting this. Okay, and then of course V gets cancelled out. So your shear center, therefore, E is independent of V, which proves it's just a geometric property. It proves that it's just a geometric property. And so E equals, or the shear center distance equals just it's now just a job of big simplification. So I'll just write the final it's not strictly speaking very simple, but I have just kind of collected how many how many terms that I can collect. H plus b minus c plus b into 3bh square minus 8c cube. Okay, so this is the expression for the shear center. Okay, and this is the expression, and as long as I get positive values for E, that means it is true that my shear center lies no on the left of my uh, web center. Okay, as long as they are positive values, I mean, it means the shear center will lie left of the shear. Positive implies lies to the left of web center. Now, what you can do is you can from this you'll be able to get for a simple channel, for a simple plane channel, c equals to 0, and if I just substitute c equal to 0 into this equation, I get nothing but, oh, I'm sorry, there should not be a v here. There you go. Okay, so I will get, so this will be 0. This is the only thing that will exist. So 3b square h square t by 12i, or b square h square t by 4i. So this is the expression for a channel, for plane channel. Okay, so since I got this result, I'm kind of confident that what expression you got above is correct. Let's also verify it with some typical example. So if I have a hat section of let me just see what I had, 50 10 31.5. Okay, so 50 into 30 into 10 into 1.25, where this is HBCT. So if I am just looking at my code IS811. Okay, so here this code gives me these values. IXX is 7.05 into 10 power 4 centimeter in centimeter per 4, and anyway these things are in mm. Okay, and my according to them, my uh, e value should be 20.2. So my e value 20.2 mm from this point. Okay, so now if using the above formula, so the above expression gives E equals, you get a slight difference, you get 18.7 mm, and the reason for this is probably, your IS811 sections will have, the corners will be like this. You have rounded corners, and this formula neglects rounded corners. Okay, so the formula neglects rounded corners, so law neglects, so therefore now you have this marginal difference between the shear center values. Okay, but otherwise, no, I have checked it for 2 or 3 more cross sections from IS811. Most of them have this small variation, so anyway the formula is valid. So anyway, this is the meaning of shear center. Basically, it's a point where your external load should be applied so that the cross section in the moments inside the plane of your cross section are all balanced out. If it's an open section, it's going to be lying either, it won't be the CG, it will be somewhere away from the CG, possibly outside if it's a channel section. If it's a bisymmetric section, it's going to be, they are going to coincide, your CG and your shear center will both coincide. If it's a bisymmetric section, and anyway, to and you also saw an example of how you can actually try to find the shear center location. So basically, it's just repeated application of tau equals VQ by IT, then finding the overall shear force in each segment, and trying to find the shear center by equating the moment about any point on this cross section to be equal to 0, which will give you what the distance of the shear center is. Okay. So anyway, since it's a hat section, the expression and the steps are quite big. You have too many terms. For simpler sections, it will be much simpler. Okay. And anyway, so from this we are able to also get if it is a plane channel, what the shear center location will be. Okay. And also know that no for a cross section like this, your shear center will actually lie at vertex is for channels. Okay. So this is how your shear centers will be, and similarly for your, if you have an I section like this, so the center of gravity will be probably somewhere here. Okay, and once again here also it will lie on the center of gravity. Okay, because no, this thing is symmetric about its y-axis. Okay, whenever you have symmetry about y-axis, you're going to have your shear center lying on the y-axis. So SE lies on x-axis on the y-axis since section symmetric about y-axis. Okay, so this is shear center. No, it's you'll have the application of shear center in so many things like your CFS design for cold form steel design for uh, flexural torsional buckling. Okay, this is just one simple example. Anyway, so I hope you learned how to find shear center for any given cross section. So try out a few more simpler examples. Try a simple try to derive this expression by starting out from these uh, these formulae. Try to derive it by yourself instead of just using this. Start from the cross section, do the integration over S, find Q, equate it with the moment and all those things. Okay. Okay. Thank you. I hope it was useful for you.